This is a video recording for chapter 1.6 on partial fractions. Okay, in our textbook, page 30, we see this table over here which shows us examples of proper algebraic fractions and improper algebraic fractions. We are familiar with proper fractions and improper fractions from whatever we've learned in primary school. So for example, the simplest case of proper fractions, we have examples such as 1/3 or maybe 100 over 108, for example. As long as the denominator is larger than the numerator, we consider them proper fractions. And then for improper fractions, we have examples where the numerator is larger than the denominator. For example, 4 over 3, for example, 100 over 99. So these are improper fractions. Now in algebra, we have similar concepts. So from this table, proper algebraic fractions, again we'll be comparing the denominator and the numerator. However, we'll be considering only the degree of the numerator and the degree of the denominator. So in example, in part A, okay, the degree over here in the numerator, degree equals to 0. When in the denominator, the degree equals to 1. As long as the degree in the denominator is greater than the degree in the numerator, then it is considered a proper fraction, a proper algebraic fraction. So again over here, numerator, degree equals to 1, denominator, degree equals to 2. So degree in denominator still larger than degree in numerator, so it is proper. Now in part C, the degree in the numerator equals to 4, degree in the denominator equals to 5. So since the degree in the denominator is greater than degree in numerator, it is a proper algebraic fraction. Now let's consider those on the right side, where there are improper algebraic fractions. So the degree over here, 3. Degree in the denominator, 2. Since 2 is not larger than 3, then it is improper. Next case, we've got 4 as the degree in the numerator. We've got 1 as the degree in the denominator. Since 1 is not greater than 4, it is improper. Finally, we have the last case, degree, 1. Denominator, degree is 1 as well. Since 1 is not larger than 1, therefore it is also improper. Okay? So this is the summary for part 1. As long as the degree of px is less than the degree of qx, where we've got px in the numerator and qx in the denominator. As long as the degree of the numerator is less than the degree of the denominator, it is a proper algebraic fraction. Now if the degree of the numerator is greater than or equal to, or equal to the degree in the denominator, it is called an improper algebraic fraction. Okay, next page. We are familiar with this. We can express 7 in terms of 3, 2, and 1. We need to be aware of these words, dividend, divisor, quotient, and remainder, using our division algorithm. So we can do the same thing for our improper fraction. So for example, let's take a look at part 1. We've got x cubed plus 3 divided by x minus 1. It is an improper fraction, okay, because the power 3 is larger than the power 1. So now when we divide x cubed plus 3 by x minus 1, this is our quotient, and we also will be able to get the remainder. Okay, so so this is what we have when we divide x cubed plus 3 divided by x minus 1. We have the quotient of x squared plus x plus 1, and we have a remainder of 4. So we can rewrite all these terms in an equation, and that will give us x cubed plus 3 is actually equals to x minus 1 multiplied by our quotient, which is x squared plus plus 1, plus a remainder of 4. Okay, so if we choose to write it in terms of a fraction, so where we have our dividend divided by the divisor, in this case dividend is x cubed plus 3, divisor is x minus 1, I am going to divide throughout by x minus 1. This is what I will get, x cubed plus 3 over x minus 1. Take note that this is simply x cubed plus 3 divided by x minus 1. Okay, and then on the right hand side of the equal sign, I'm going to have only my quotient left, x squared plus x plus 1, and my remainder is now 4 over x minus 1. So in this case, what we have done is to change our improper fraction to become a polynomial plus a proper fraction. Okay, so this is a skill that you must have. Okay, and that is summarized over here. So this is another example from work example number 18. Here express this fraction as the sum of a polynomial and a proper fraction. Right now, it is an improper fraction where the degree is 3 in the numerator, degree of the denominator is 1. So it's improper. So now we can use our long division. Okay, x cubed plus 2x squared. Then you plus a 0x by yourself, minus 3. Carry on with your long division. And we will be able to express it, this improper fraction, as the quotient, as shown over here. This is our quotient, plus, in this case, plus the remainder. Now the remainder is negative 2, so we plus a negative 2, this is the remainder, divided by x minus 1, which is our divisor. Okay, so remainder refers to only this part. So now we have answered the question already, expressing the improper fraction as the sum of a polynomial, which is our quotient, and a proper fraction. Look at the proper fraction. Degree equals to 0. Degree equals to 1. So we have a proper fraction over here. So next, some recap on addition of fractions. This time in algebra. Okay, so 1 over x plus 1 plus 3 over x minus 2. In order to add them up, they must have the same denominator. So the denominator in this case will be x plus 1, x minus 2. So we multiply 1 with x minus 2, we multiply 3 with x plus 1, combine them together, expand, simplify. Okay, this is if you have two different linear factors. Here we have one linear factor and one repeated linear factor. Okay, what does repeated linear factor mean? In this case, it is referring to our x plus 1 square. Why do they call it repeated? Because if we rewrite it, it becomes this, x plus 1 times x plus 1. These are repeated linear factors. Okay, so here, if we see that these two fractions are added together, the lowest common multiple, the lowest common denominator will be x plus 1 squared. And we only need to multiply the fraction on our left with x plus 1. Numerator, x plus 1. So we end up with 2x plus 2 plus 1 divided by x plus 1 squared. Okay, you can ignore this part. Next, in part C, now we can also have one linear factor and one quadratic factor which cannot be factorized. Which cannot be factorized. Which kinds of quadratic factors cannot be factorized? Those that look like this. X squared plus. It must be a plus something. So for example, x squared plus 3, x squared plus 1, x squared plus 10. All these cannot be factorized. So you simply expand it out and simplify to get the answer. Now in partial fractions, we are going to go the other way. We're going to reverse whatever we have done. So in part A, when you are given 4x plus 1 divided by x plus 1, x minus 2, we are going to work backwards to give us this. We are decomposing the fraction into smaller fractions. So similarly, from here, you are expected to work backwards. From here, you work backwards to get partial fractions. Okay? Okay, in case 1, where we have proper fractions with distinct linear factors in the denominator. So our denominators will be different linear factors. So let's take a look at part A. We are given two fractions, 1 over x plus 1 plus 3 over x minus 2, both of which are linear, and they have linear factors in the denominator, and they are proper fractions. Okay, when you combine them together, we get another fraction on the right side. This time, the denominator looks like this, x plus 1 times x minus 2. These two are different factors. And look at the numerator, we end up with 4x plus 1. The degree in the numerator is 1. The degree in the denominator, 2. Okay? Now, in the case of part B, our fractions, when we start off with 2 over x plus 3 minus 4 over 2x minus 5, again they are proper fractions. When we combine them, we end up with, over here, numerator degree equals to 0, in the denominator degree equals to 1, equals to 2. So in both cases, our degree, whatever we end up with, after we add them up, after we add the fractions up, the degree of the numerator will always be less than the degree of the denominator. Okay, so trying to work backwards. If I try to work backwards, when we are given this, in our denominator, we have, over here, ax plus b plus cx times cx plus d. Okay, so ax plus b, cx plus d. So we try and draw a parallel between our results over here with this general form. The denominator will look like this, ax plus b times cx plus d, where the values of a, b, c, and d are constants. Okay, so now we are going backwards. What is in our numerator? The numerator will have a degree that is less than 2. Okay, look at the first example, the degree is 1. In the second example, the degree of the numerator is 0. The degree will be less than 2. So generally, how shall we write it? We write px plus q. Okay, px plus q. Now this over here is degree equals to 1. The degree is 1. If we compare it with part A, the value for A will be 1. The value for B will be 1, positive 1 again. The value for C is actually 1. And the value for D, okay, I can't really see clearly. The value for D is actually, let me choose another color, orange. Okay, not very clear too. Okay. Negative 2 over here. Right? So now the value for P, we've got, let's use another green. The value for P in this case will actually be 4, and the value for Q is, in this case, positive 1. So this is the general form, px plus q over ax plus b times cx plus d. We are going to decompose this into fractions, linear fractions, as shown on the left hand side. Okay, so we expect it to become a over x, ax plus b plus b over cx plus d. Okay, notice that the denominator over here, ax plus b, came from here, and our other denominator, cx plus d, came from here. How do I decide that the numerator is going to be a? Why can't it be why must it be a constant? Why can't it have an x term? Similarly for this, why must it be b? Why is it a constant? Why can't I have an x term? Reason is because over here, in these two examples, our numerators are all constants. They are all one for their degrees, they are all 1 less than the degree of the denominator. All of them, they have denominator, they are linear, degree 1. So in the numerator, the degree is reduced by 1 to be 0. That leaves us with a constant. In summary, when we are given a fraction like this, made up of two linear factors in the denominator, we are expected to be able to rewrite it to become this form, where capital A and capital B, they are unknowns to find out. The small a, small b, small c, small d are simply copied from here. Okay, so now it is best to try with an example. You may read work example 19 to see how it is done. I will give you another example that is from practice now 19. Okay, question 1. Express 9x minus 5 over x minus 3, x, 2x plus 5 in partial fractions. Okay, so this is our question. Straight away, my first step, I see that, oh, the denominators are already factorized. The denominator is already factorized. We have got two linear factors. So straight away I say let 9x minus 5 over x minus 3, 2x plus 5. I let this be equals to, remember from over here, I've got px plus q over ax plus b, cx plus d. I let it be equals to a, capital A, over one of the factor, plus capital B over the other factor. So in this case, it will be a over x minus 3 plus b over 2x plus 5, where capital A and capital B are unknowns to be determined. So now the challenge is to find capital A and capital B. We've got a few approaches that we can use. I find that the easiest way is to multiply throughout by this entire denominator. What happens if I multiply throughout by this denominator? Let's take a look. I do it step by step without skipping steps. Okay, so on the left hand side, I've got originally 9x minus 5. 9x minus 5 divided by x minus 3, 2x plus 5. So this is supposed to be equals to a over x minus 3 plus b over 2x plus 5. I'm going to multiply throughout by the denominator. Okay, so multiplying throughout on this side, I'll be multiplying x minus 3, 2x plus 5. And we all are very clear of what happens after that. They are going to cancel, okay? So I'll leave the cancellation to later. Since I multiply the left hand side by x minus 3 and 2x plus 5, I must also do the same for the right hand side. So over here, x minus 3, 2x plus 5. Okay, multiplying throughout. Likewise over here, x minus 3, 2x plus 5. These two, the left hand side will still be equal to the right hand side, because whatever I did to the left, I've done on the right. Now it is time to cancel. X minus 3 with x minus 3, 2x plus 5 with 2x plus 5. We knew that already. Here we have x minus 3 and x minus 3, 2x plus 5 and 2x plus 5. So what are we left with now? We are left with the numerator 9x minus 5 equals to a times 2x plus 5 plus b times x minus 3. Okay? Compare this with the original question. You should be able to see some patterns. In fact, this step over here can be skipped. Straight away, you could have done this mentally. I am going to leave only the numerator, which is 9x minus 5, and it is going to be equals to a multiplied by the entire denominator that is highlighted in green divided by x minus 3. Of course, I'm going to have 2x plus 5 left, and I'm going to have plus a b times x minus 3. You can do this step. You can do the previous step, all the cancellation mentally. What's important is that you obtain this. Now from here on, obtaining the value of a and b is very straightforward, and we are familiar with it already. Okay, we could let x be equals to 3. When we let x equals to 3, b will disappear. The b term will disappear. Okay, so one presentation, we can let x be equals to 3. Okay, so the intention of letting it become 3 is so that this will become 0. Okay, so when I let x be equal to 3, I've got 9 times 3 minus 5 is supposed to be equals to a times 2 times 3 plus 5. And the right hand side, we've got, if we want to continue, plus b 3 minus 3. But we don't have to write that down because we intended for it to be 0 anyway. So we've got 27 minus 5, that's 22, equals to a times 11. A must therefore be equals to 2. Now that I know a is equals to 2, it makes things easier to find the value of b. Alternatively, I can always let x be equals to negative 5 over 2. Okay, when x equals to negative 5 over 2, I will end up with 9 times negative 5 over 2 minus 5 equals to, the entire a portion disappears, b times negative 5 over 2 minus 3. Continue with your work, you should end up with b. Continue with your work and you should end up with b equals to 5. This is not the only way to do it. There are other ways that you can try. You can let x be something else. You can even compare the coefficients if you like. Okay, so finally, we have found the values of a. We found the values of b. We need to substitute them back in. Okay, so our final statement will therefore be 9x minus 5 over x minus 3, 2x plus 5 is now equals to the value of a being 2 over x minus 3 plus 5 over 2x plus 5. And this is our final answer. Now, please take some time to do question 2 of try it or practice now 19. Okay, and after practice now 19 question 2, we're going to take a look at the second case where we have repeated linear factors in the denominator. So what does that mean? Instead of having px plus q over ax plus b times cx plus d, which we are able to write down that this is equals to a over ax plus b, capital A and small a have no relationship at all, plus b over cx plus d. Instead of this case, we're going to consider the next case, px plus q over, now the denominator looks like this, ax plus b squared. It is a repeated linear factor. This part you've memorized already. The next thing to memorize will therefore be this. This is equal to a over ax plus b plus b over ax plus b squared. The explanation is given on page 35. Go and read it yourself and understand it. If you cannot, you are not expected to be able to derive it. But understanding helps in memorizing. Okay? If all else fails, you can simply memorize this. When you see the denominator having a repeated linear factor, you must be able to write down that it is decomposed into a, capital A over ax plus b plus capital B over ax plus b squared. So we're going to do you're going to read the example, read work example 20 while I do practice now 20 question 1. Okay, so this is the question for question 1. Expressed again in partial fractions, we got 5 minus 15x over 2x plus 1 squared. Straight away, you must be able to write down this is equals to a over 2x plus 1 plus b over 2x plus 1 squared. Then multiply throughout by the denominator, which is 2x plus 1 squared. We're going to end up with 5 minus 15x equals to a times 2x plus 1 plus b. You can use either substitution of values in, you can use observations, up to you. We should find that 2a, which is the coefficient of x, must be equals to negative 15. That gives us a equals to negative 15 over 2. And now, the value for b. If I consider the constant terms, on the left, the constant term is 5. On the right, the constant term will be made up of negative 15 over 2, which is the value of a, multiplied by 1 plus b. So therefore, b must be equals to 5 plus 7.5. That gives us 12.5, which is 25 over 2. So I've got the values for a, I've got the values for b. Substitute them back into the equation. So 5 minus 15x over 2x plus 1 squared must give me negative 15 over 2 times 2x plus 1. Okay, I did some manipulation over here. And plus the value of b. Okay, that is 25 over 2 times 2x plus 1 squared. And this is my final answer. So your turn now to practice now 20, question number 2. After you're done with practice now 20, question number 2, I want you to read work example 21, where we have in the denominator 2x plus 3 and x minus 1 squared. In our numerator, we have 10 minus 3x minus 2x squared. Before we break this down into the partial fractions, I need you to check that it is a proper fraction first. Degree in the numerator is 2. Degree in the denominator is 3. Okay, good. It is a proper fraction. Now we are able to decompose it. When we decompose it, we do it step by step. I've got a linear factor over here, so I'm expecting a over 2x plus 3. Plus, I've got a repeated linear factor over here. So I'm expecting b over x minus 1 plus c over x minus 1 squared. From here on, all the steps are the same. Okay, so I will move on to practice now question 21. Practice now 21, question number 1. Express 4x squared plus 5x minus 32 over x plus 2 square x minus 11 in partial fractions. First, check. Proper fraction? If it is proper fraction, carry on. If it is not proper fraction, you need to do your long division. You need to break it down into a polynomial plus a proper fraction. In this case, the numerator has degree 2, denominator has degree 3. So it is proper fraction. Let us now decompose it. From the first one, denominator x plus 2 square, I can decompose it to become a over x plus 2. Since it is repeated, I will have b over x plus 2 square plus c over x minus 11. This is my first step. Now multiplying throughout by the denominator, I will have 4x squared plus 5x minus 32 equals to a times x plus 2 x minus 11 plus b x minus 11 plus c multiplied by x plus 2 square. This is now my polynomial. Okay, this is now what I have to find out. For the values of a, B, and C. There are different methods that you have learned already. I think the easiest method is to substitute the value of x equals to 11, because when I substitute x equals to 11, this disappears, I'm only left with C. I can find C straight away. I can also substitute x equals to -2. This disappears, I'm left with B. And from the final value, the final unknown, which is B, I can simply substitute x equals to 0 if I like. Okay, so sub x equals to 11. That is 4 times of 11 square plus 5 times of 11 minus 32 equals to, on the right hand side, this disappears, I'm left with C 11 plus 2 square. Okay, so 4 times of 121 plus 55 minus 32 equals to C times 169. This tells me that C is equals to 3. So this value over here will be actually 3. So you can next sub x equals to -2 to find the value of, this one disappears to find the value of B equals to something. And finally, you can also sub x equals to 0 to find the value of A. Okay, so try it yourself. Similarly, practice now 21 question 2. Practice now 21 question 2. The final part of the next case that we have is case number 3, where the denominator has a quadratic factor that cannot be factorized. So I will leave that to Friday. So what I have in this 30-minute video so far will be work that is meant to be covered on Thursday for your 2-period lesson. Use the remaining time to do all the practice now questions. Your homework from exercise 1F. Okay, from exercise 1F, we've got question 3 and 5. Just 2 questions only.